Hello my friends and welcome back to the FUTech HD channel. The raw mix analyzer in a steel mill is designed for fully automatic sampling and analysis of granulated sinter feed, which is crucial for maintaining the quality of raw materials for iron production. The system includes a sample-taking robot and a series of analysis systems housed in an enclosed space near the raw mix conveyor belt, where the material is fed onto the sinter machine. The robot automatically collects samples from a consistent spot in the material stream every 10 minutes, ensuring standardized and uniform sample preparation and analysis. The primary characteristics measured include moisture content, permeability, and bulk density, though the system can also analyze other properties based on customer requirements. Additional samples can be made available for manual testing if needed. The data from these measurements are fed into a Level 2 expert system, which optimizes process parameters. This system allows for immediate corrective adjustments, such as altering the water addition to the sinter raw mix, to maintain stable process conditions and optimized operations. The benefits of this fully automatic and standardized sampling system include increased plant productivity, high and stable sinter quality, rapid response to changing process parameters, and improved operator safety. The robotic system also enhances flexibility in selecting raw materials, particularly fine and ultra-fine iron ores. The robust design of the raw mix analyzer enables it to withstand the harsh conditions of a sinter plant, significantly improving sinter process control and the production of high-quality sinter. At the Voestalpine pilot plant in Linz, Austria, a groundbreaking dry slag granulation process with heat recovery is being tested. Globally, approximately 400 million tons of blast furnace slag are produced annually. Traditionally, this slag is either dumped or cold quenched with water to form a granulated product for the cement industry. However, this method results in a significant loss of the heat energy contained in the molten slag. Maximizing energy efficiency is a critical goal in the iron and steel industry. A key strategy to achieve this is to recover the energy from molten blast furnace slag through a dry granulation process, while also producing high-quality granulated slag for cement production. In this process, molten slag at a temperature of 1,450 degrees Celsius is tapped from one of the blast furnace's 3 tap holes and directed into the granulator at a rate of approximately 1 ton per minute. The slag is then dropped onto a rapidly rotating disc, where it is granulated and cooled by an ascending airstream. The granulated slag is collected at the bottom of the vessel, while the cooling air exits at a temperature suitable for generating superheated steam. This steam can be used for various applications within the steelworks, including electricity generation, thereby recovering a significant portion of the energy from the molten slag. The EAF Quantum represents a new evolution in electric steelmaking technology, combining advanced processes and energy-saving solutions to meet the current demands for sustainable and efficient steel production. Developed by Primetals Technologies, the EAF Quantum offers significant advantages in terms of productivity, efficiency, and environmental impact. Key features and advantages of EAF Quantum. Optimized preheating and melting concept. The EAF Quantum is designed to optimize the preheating and melting of scrap materials, which is crucial for reducing energy consumption and improving overall efficiency. The furnace employs a unique trapezoidal shaft design and a redesigned retaining system to ensure optimal scrap distribution and efficient off-gas routing. This design facilitates effective heat transfer and maximizes the recovery of energy from the preheated scrap. High energy efficiency. One of the standout features of the EAF Quantum is its ability to preheat 100% of the scrap, which significantly lowers energy consumption. The furnace achieves energy consumption rates of less than 280 kilowatt-hours per ton of steel, making it one of the most energy-efficient electric arc furnaces available. This efficiency is achieved through the innovative design of the furnace and the effective use of recovered energy from the off-gas. Improved melting process. The EAF Quantum enhances the melting process by utilizing large liquid heels, which allow for pure flat bath operation. This method minimizes electrical flicker and supports the efficiency of the preheating process. The result is a more stable and efficient melting operation, which contributes to higher productivity and reduced energy costs. Advanced Slag-Free Tapping System, FAST. The furnace incorporates the Furnace Advanced Slag-Free Tapping, FAST, system, which employs a siphon design to enable charging, tapping, and tap hole refilling under power-on conditions. This system enhances the efficiency of the tapping process and minimizes downtime, further boosting the overall productivity of the furnace. Environmental compliance. The EAF Quantum is designed with environmental sustainability in mind. The efficient recovery of energy and the optimized melting process reduce the overall environmental impact of steelmaking. The furnace's design also ensures compliance with stringent environmental regulations, making it an attractive option for steel producers aiming to minimize their ecological footprint. Additional technologies and innovations. The EAF Ultimate represents the pinnacle of electric arc furnace technology, offering maximum productivity and flexibility. It features extremely high energy input rates, innovative RCB technology to enhance performance, and an enlarged furnace for single bucket charging. These features result in very short tap-to-tap times and significantly boost productivity. Designed to meet the increasing global demand for stainless steel, the EAF Stainless combines the advantages of the EAF Ultimate with the specific requirements of stainless steel production. This furnace type maximizes power input and productivity, making it the leading choice for producing high-quality stainless steel. The 350,000 tons per year Endless Casting and Rolling (ECR) plant is a state-of-the-art facility designed for efficient and competitive production of rebar products. This plant employs advanced technology and innovative processes to enhance productivity and quality while minimizing costs. Modern mini-mills incorporate integrated processes from direct reduced iron, dry, plants, electric arc furnaces, EAFs, and continuous casting and rolling. Continuous billet caster for hot charging. The plant features a continuous billet caster that supports hot charging, optimizing energy efficiency and reducing reheating needs. This system is tailored for producing square billets of 150 by 150 millimeters, which are ideal for further processing. Low and medium carbon steel. The ECR plant primarily processes low and medium carbon steel, ensuring versatility in the types of steel products it can produce. This focus allows the plant to meet various market demands, particularly in construction and infrastructure sectors. Induction furnace and roughing mill. An induction furnace is utilized to heat the billets to the desired temperature before they enter the roughing mill. The roughing mill consists of 6 SHS, split housing stand, housingless stands, which provide robust and precise rolling capabilities. This configuration enhances the uniformity and quality of the rolled products. Intermediate and finishing mill. Following the roughing mill, the billets pass through intermediate and finishing mills. These mills are crucial for achieving the final dimensions and surface finish of the steel bars. The entire rolling process is meticulously controlled to maintain high standards of product quality. Inline QTB treatment. The plant incorporates an inline QTB, quenching and tempering bar, treatment system for deformed bars. This process significantly improves the mechanical properties of the bars, such as strength and ductility, making them suitable for demanding applications. Cooling bed and cold cutting. A 66 by 6 meters rake-type walking beam cooling bed is used for controlled cooling of the bars. Bar counting and bundle forming. Automated systems count the bars and form them into bundles. These bundles are then tied and prepared for shipping. Bolts and nuts are ubiquitous components in modern manufacturing, playing a critical role in the assembly and functionality of countless products. Their development has paralleled advancements in engineering and materials science, evolving from simple wooden fasteners to sophisticated, high-strength alloys used in high-stress applications. This evolution has been crucial in enabling the precision, durability, and reliability required in contemporary manufacturing industries. Historical development. The use of bolts and nuts dates back to ancient civilizations. Early examples were simple wooden pegs and wedges used in carpentry. Metal fasteners emerged during the Bronze Age, but it was not until the Roman era that more refined screw threads were developed. The Industrial Revolution in the 18th and 19th centuries marked a significant turning point. The introduction of mass production techniques and the invention of machinery like the screw-cutting lathe by Henry Maudslay in 1800 revolutionized bolt and nut manufacturing. This innovation allowed for the production of standardized threads, which greatly improved the interchangeability and compatibility of fasteners. Modern manufacturing processes. Today, bolts and nuts are manufactured through a variety of advanced processes. Cold forging is one of the most common methods, where wire is cut to length, heated, and then formed into shape using dies. This process ensures high strength and precision. Additionally, thread rolling, a method that displaces material to form threads rather than cutting them, is widely used because it produces stronger threads and smoother surfaces. Materials used in bolt and nut production have also evolved. While carbon steel remains the most common material, alloy steels, stainless steels, and exotic alloys like Inconel are used for applications requiring high strength, corrosion resistance, or high temperature tolerance. For instance, grade 8 bolts, made from medium carbon alloy steel, are heat treated to achieve a tensile strength of 150,000 psi, making them suitable for heavy machinery and automotive applications. Role in modern manufacturing industries. Bolts and nuts are essential in numerous sectors, including automotive, aerospace, construction, and electronics. Their importance can be illustrated through several key functions. Structural integrity. In construction, bolts and nuts are critical for the structural integrity of buildings, bridges, and infrastructure. High-strength bolts are used in steel frameworks to ensure stability and safety. For example, ASTM 325 bolts, which can withstand tensile loads of up to 120,000 psi, are commonly used in structural applications. Automotive industry. The automotive industry relies heavily on bolts and nuts for assembling engines, chassis, and body components. Precision and strength are paramount, as these fasteners must endure high stress and vibration. Automotive manufacturers often use bolts with specific grades and coatings to resist corrosion and wear, ensuring long-term reliability. Aerospace industry. In aerospace, the demands are even higher. Fasteners must be lightweight yet strong enough to withstand extreme forces and temperatures. Titanium bolts, which offer an excellent strength-to-weight ratio and corrosion resistance, are commonly used. For instance, the Boeing 787 Dreamliner utilizes approximately 2.3 million fasteners, many of which are specialty bolts and nuts designed to meet rigorous aerospace standards. Electronics. In the electronics industry, miniature bolts and nuts are used to assemble components with precision. These fasteners must be manufactured to tight tolerances to ensure proper fit and function. Stainless steel and brass are frequently used materials due to their corrosion resistance and electrical conductivity. Heavy machinery. Bolts and nuts used in heavy machinery must be able to withstand immense loads and harsh operating conditions. Bolts such as ASTM A193 grade B7, with a tensile strength of 125,000 psi, are employed in high-pressure and high-temperature environments, such as in oil and gas applications. Technological advancements. The manufacturing of bolts and nuts continues to advance with technology. Computer numerical control, CNC, machining allows for the production of highly precise fasteners with tolerances within micrometers. Automation and robotics have increased production efficiency and consistency, reducing human error and manufacturing defects. Furthermore, advancements in material science are leading to the development of new alloys and coatings that enhance the performance of bolts and nuts. For example, ceramic coatings can improve wear resistance and reduce friction, extending the lifespan of fasteners in demanding applications. Quality control. Quality control is crucial in bolt and nut manufacturing. Standards organizations such as the American Society for Testing and Materials, ASTM, the International Organization for Standardization, ISO, and the Deutsches Institut für Normung, DIN, set stringent guidelines for material properties, dimensions, and performance. Manufacturers employ various testing methods, including tensile testing, hardness testing, and corrosion testing, to ensure their products meet these standards. We're in ISAC, a leading company specializing in hot forging for 40 years, operates from its facility in Busano, located in the province of Turin. The production process begins in the raw materials department, where various qualities of steel are stored according to the section of the bars. Each bar is encoded with a barcode and tracked electronically from arrival to the reheating furnace. Bars are loaded and welded on the bench for entry into the furnace and subsequently heated. An optical pyrometer measures the temperature as the bars exit the furnace, and the data is plotted on a graph. The bars are then cut into required lengths, and a preform is made on the press according to the shape of the final product. Next, the forging phase takes place using power hammers. ISAC can produce a wide range of customer-designed products with hammers ranging from 16,000 to 31,000 kgm, with unit weights varying from 15 to 200 kg. The hammers are equipped with anti-vibration systems capable of reducing ground-transmitted vibrations by 90%. The forged piece then undergoes deburring on a press, and the finished products are transported via conveyor belts to designated bins. The company's production of mechanical components mainly caters to the heavy vehicle sector, including industrial vehicles and earth-moving machinery. A final visual inspection is conducted on all products before they are packed according to customer specifications and shipped. Within the production facility, there is a dedicated technical and quality control office strategically positioned to continuously monitor production. This office also handles the design of molds using 3D simulation software, which are then produced in a specialized department equipped with automated and numerically controlled machinery. The production of axles is a complex process that involves several advanced machinery processes to ensure the final product meets the required specifications for strength, precision, and durability. Each machine plays a crucial role in shaping and forming the axle, contributing to its overall quality and performance. Reducing and expanding presses, also known as swagers, are integral in shaping the axle tubes. During the forming process, the tube is held axially by at least 2 clamping jaws. A guided drawing in ring or an expanding mandrel is then pushed into or over the tube, causing the workpiece to either expand or reduce in diameter. The closed design of the machine housing ensures durability, protecting the internal components from external factors. This design also provides consistently high precision due to robust construction and precise control of the forming tools, and allows easy access to the tools, facilitating quick changes and maintenance. This process is essential for ensuring the axle tubes meet specific diameter and thickness requirements, which are vital for the overall strength and performance of the axle. The high-speed end forming process is based on the spinning or flow forming principle but utilizes a pot-shaped tool instead of a roller. This tool contains the entire shape profile and is used to shape the end of the axle tubes, ensuring they are rotationally symmetrical and meet design specifications. This method is faster than traditional methods, reducing production time and ensuring consistent and precise end forming. This process is crucial for creating the ends of axle tubes that need to be perfectly symmetrical for proper assembly and function in vehicles. Forging machines use 2, 3, or 4 jaw tools to exert radial compressive forces on a rotating workpiece. The tool segments shape the workpiece by compressing it radially, and this process can be done either hot or cold, depending on the material and the required degree of forming. Forging machines are versatile and suitable for various metals, including steel, aluminum, copper, and titanium. The forging process increases the strength of the material by refining its grain structure, making it ideal for creating various shapes and sections of the axle, such as flanges and bearing seats, which need to withstand high stresses and loads. Upsetting machines involve partially heating the tube and then enclosing it with 2 die segments. Material is then axially compressed by 1 or 2 punches. This process can form both tubular and solid materials, allowing for the creation of complex contours based on the tool geometry. Upsetting allows for the formation of intricate shapes with high precision and can handle a variety of materials and shapes. It is used to form specific features on the axle, such as thickened ends or flange-like structures, which are critical for the assembly and performance of the axle. Bending machines are used to flatten and pre-bend cross-rolled or stretch-rolled aluminum bars. This process combines several forming steps, flattening, bending, and flattening, into one movement, significantly reducing secondary scrap. The combination of multiple steps into one movement saves time and reduces production costs while minimizing waste by reducing flash and secondary scrap. These machines form the complex bends and shapes required in the axle, ensuring they fit perfectly within the vehicle's suspension system. The comprehensive monitoring double-axle friction welding machine is an advanced piece of equipment designed for the precise and efficient welding of axles. Here's a detailed overview of how it works, operation and structure. The machine features a unique double bed structure, providing ample operation space for handling large axle components. This design enhances accessibility and maneuverability during the welding process, allowing operators to work more efficiently. Clamping and positioning. A critical aspect of the machine is its brand new axle housing clamping and positioning device. This device ensures that the axle components are held securely and precisely in place throughout the welding process. Proper clamping and positioning are crucial for maintaining the alignment and integrity of the weld, preventing defects, and ensuring the structural strength of the welded axles. Hydraulic drive system. The machine is equipped with a high-quality hydraulic drive system that delivers stable power output. This hydraulic system is responsible for generating the necessary force and torque required for the friction welding process. The stability and reliability of the hydraulic drive ensure consistent welding performance and high-quality welds. Friction welding process. In friction welding, the machine rotates one of the axle components while the other remains stationary. The components are then brought into contact under pressure. The friction generated at the interface produces heat, causing the material at the joint to soften and become plastic. Once sufficient heat is generated, the rotation stops, and the components are forged together under pressure, creating a strong, solid-state weld. Comprehensive monitoring system. The machine includes a comprehensive monitoring system that tracks, records, and stores welding data. This system allows operators to monitor key parameters such as rotational speed, pressure, temperature, and welding time in real time. The recorded data can be easily accessed and analyzed to ensure the welding process meets the required specifications and to improve quality control. This monitoring capability enhances the reliability and traceability of the welding process, making it easier to identify and address any issues that may arise. Here, Detroit axles for heavy and medium-duty commercial vehicles are meticulously engineered, embodying a standard of quality that starts from the ground up. What sets the facility apart is their innovative use of needle bearings, a design choice that minimizes friction and wear compared to traditional bushings. Combined with a watertight knuckle assembly, this engineering ensures not only reduced maintenance but also significantly prolongs the lifespan of each axle. Trusted globally in millions of trucks, the facility offers a comprehensive range tailored to meet diverse needs, from robust rear axles for heavy-duty applications to versatile models designed for smaller-scale operations. Performance optimization is at the core of the facility design philosophy. Their axles feature customized steel compositions that enhance durability while reducing weight, alongside gear sets engineered for maximum strength and minimal distortion. An integrated ring gear further consolidates parts, enhancing compactness and efficiency. The differential design employed by the facility sets benchmarks in stability and robustness, ensuring unparalleled reliability on the road. Precision machining is pivotal to the production of the facility rear axles. Utilizing a state-of-the-art power dry cutting process, gear sets are meticulously crafted to tolerances measured in 10,000ths of an inch. This precision not only ensures perfect alignment but also underscores the facility's commitment to environmental sustainability, as this process eliminates the need for coolants and reduces machining time by half compared to traditional methods. Heat treatment is another critical facet of the facility, manufacturing excellence. Advanced vacuum carburizing and high-pressure gas quenching processes are employed to strengthen gear components. This innovative approach minimizes heat emissions and energy consumption, distinguishing the facility as a leader in environmentally conscious manufacturing practices. Quality assurance is paramount throughout the facility production line. Highly trained technicians rigorously inspect and gauge each component, employing torque control and electronic checks to guarantee adherence to stringent quality standards. Error-proofing measures are integrated into every stage of assembly, ensuring flawless execution and product integrity. To validate performance, the facilities subject their axles to rigorous testing protocols, including simulations that replicate 1.2 million miles of real-world driving conditions, a testament to their commitment to delivering reliability under the most demanding circumstances. Every part manufactured by the facility is meticulously tracked and monitored through advanced coding and vision systems. This ensures that only components meeting exact specifications proceed through the assembly process. Supported by comprehensive quality feedback loops and a robust warranty program, Detroit Axles provide customers with unparalleled confidence in their product's reliability and longevity. The new desulfurization station at ArcelorMittal Monlevade in Minas Gerais, Brazil, is a pioneering solution designed to enhance productivity, lower costs, and reduce emissions. It achieves sulfur levels below 0.005%, minimizes desulfurization agent consumption, and reduces processing times to under 30 minutes. This station is unique as it combines a volumetric dosing device for magnesium, Mg, with a lime, Sal, injection dispenser, allowing for flexible injection ratios from 2 to 1 to 10 to 1. ArcelorMittal Monlevade, with an annual production capacity of 1.2 million tons of steel, sought Primetals Technologies' expertise to upgrade its hot metal desulfurization process. Previously, desulfurization using torpedo cars was costly and time-consuming. The new system, integrated into the 130-ton hot metal charging ladle, facilitates precise control over magnesium and lime injections. The volumetric dosing device ensures accurate injection of 3 to 15 kilograms of magnesium per minute, leading to lower agent consumption and shorter processing times. Alongside the desulfurization station, Primetals Technologies supplied auxiliary equipment, including a deslagging machine, a ladle transfer car, and a storage and dedusting system with a suction capacity of approximately 900,000 cubic meters per hour. Slab casting technology is a pivotal advancement in steel manufacturing, offering a comprehensive range of integrated equipment and system solutions that ensure high productivity, quick startups, short ramp-up times to full production, and maximum casting flexibility. Primetals Technologies, one of the original pioneers in this field, has demonstrated its expertise through recent advancements in automation solutions like Dynaphase, Dynix 3D, and Dynagap Soft Reduction 3D. These dynamic secondary cooling and soft reduction packages consider thermodynamic effects such as shrinkage and phase transitions, significantly enhancing the quality of the solidification phase in the continuous casting process. This leads to direct improvements in slab quality. Additionally, the Mold Expert Breakout Predetection system increases plant availability and reduces maintenance time by providing prompt alarms. Its superior performance has made it the leading system for mold monitoring worldwide, with nearly 200 installations. This beast machine is cutting through 500 mm thick S355J2 plus N material with precision and efficiency. This robust machine handles the substantial thickness with ease, ensuring high-quality cuts that meet stringent industry standards. BGH Primetals in Germany integrated a new Argon Oxygen Decarburization (AOD) converter into its existing steel plant to enhance energy and resource efficiency. This integration secures flexible production, reduces specific consumption of raw materials, refractory materials, and electrical energy, and boosts productivity by shortening treatment times. Additionally, the AOD converter improves the quality of the end products. Primetals supplied the 50-ton converter, along with the alloy and aggregate system, primary gas cooling system, and automation systems. Continuous casting involves tasks performed close to liquid steel, traditionally requiring operators to work in hazardous environments. The LiquiRob robot system from Primetals Technologies automates these tasks, significantly enhancing safety and advancing the goal of manless casting. Operators can now control the robot remotely, staying at a safe distance from the molten steel. Liquorob's automated functions are focused on the ladle and tundish areas. In the ladle area, Liquorob can mount the slide gate cylinder automatically, eliminating the need for human intervention. It also connects essential media couplings on the ladle, including pneumatics for slide gate cooling, argon sealing, and electrical signals for the slag detection system. In the tundish area, Liquorob performs 8 critical tasks: shroud manipulation and cleaning, tundish powder feeding, measurements, various samplings, and oxygen lancing. The automatic shroud manipulation, guided by a 3D camera system, allows Liquorob to accurately position and handle the shroud, providing a safer and more effective solution compared to semi-automatic systems. The innovative bayonet coupling system ensures the ladle turret is free of rigid connections during casting, which facilitates turret turning in emergencies. If a new ladle fails to open readily, the fully automatic opening system intervenes, further reducing the need for human presence in dangerous situations. Feeding tundish powder, another risky task, is also automated. Liquorob can feed up to 90 kilograms of powder in various positions on the tundish using a single shovel. The system's powder silo can hold several tons of material, ensuring continuous operation. Liquorob enhances measurement accuracy and sample taking. Equipped with a custom-built tool changer, the same robot used for shroud handling can measure temperature, hydrogen content, and perform other probe operations. In a 10 inches rolling mill, the cog station is integral to the process of transforming a 2.50 square bar into a 1.167 round bar. This procedure begins with the square bar, which is approximately 3 to 4 feet long. The bar is first heated to a high temperature, making the metal malleable. The heated bar is then fed into the rolling mill through the cog station, which ensures precise alignment and consistent feeding. The rolling mill consists of a series of grooved rolls that gradually shape and elongate the metal bar. As the bar passes through each set of rolls, it undergoes a reduction in cross-sectional area and an increase in length. The cog station is crucial here, as it maintains the correct positioning and feed rate, ensuring that the bar is evenly processed. With each pass through the rolls, the bar's dimensions are progressively reduced. The transformation from a square to a round cross-section requires precise control of the rolling process, with each roll set designed to make incremental changes to the bar's shape. This method ensures that the final product has a uniform diameter and consistent mechanical properties. By the end of the rolling process, the initial 2.50 square bar has been elongated to approximately 24 feet and reshaped into a 1.167 round bar. This significant transformation not only alters the bar's dimensions but also enhances its mechanical properties, making it suitable for various industrial applications. The efficiency and precision of the cog station and rolling mill are critical in achieving the desired quality and specifications of the finished round bar. Track bolts, also known as rail bolts, are essential components in the railway industry, used to fasten steel rail ends together at joints. Their sizes vary depending on the specific requirements of the rail section, with the proper diameter and length determined by applicable railway standards. Track bolts come in several types, including button head oval neck track bolts, diamond neck track bolts, rail bolt NFF 50008, fish bolts, Russian standard track bolts, clip bolts, clamp bolts, anchor bolts, T-bolt clamps, and other special bolts. The manufacturing process of high-quality track bolts begins with material selection. High-strength steel is typically chosen for its superior tensile strength and toughness, necessary to withstand the significant forces exerted during rail operations. The selected steel must meet stringent industry standards to ensure durability and reliability. Once the material is selected, the forging process commences. Steel rods are heated to high temperatures and shaped into the desired bolt form using a forging press. This step is crucial as it imparts the required mechanical properties to the bolts, such as strength and durability. After forging, the bolts undergo thread rolling, where the threads are formed by rolling rather than cutting. This enhances the bolt's fatigue strength and provides a smoother surface finish. Following thread rolling, the bolts are subjected to heat treatment, a critical step for enhancing their mechanical properties. Through a series of heating and cooling processes, the bolts achieve the desired hardness and tensile strength. Common heat treatment methods include quenching and tempering. To further prevent corrosion and increase the longevity of the bolts, surface treatments such as galvanizing, plating, or coating are applied. This ensures the bolts can withstand harsh environmental conditions. Quality control is integral to the manufacturing process, with track bolts undergoing rigorous inspection and testing to ensure they meet industry standards. These tests include dimensional checks, tensile strength testing, hardness testing, and surface finish inspections. Only bolts that pass these stringent tests proceed to the application phase. In application, track bolts must be of the correct size and tightly installed. Each joint requires at least 2 track bolts in each rail, tightened to approximately 400 foot-pounds of torque, developing between 25,000 and 30,000 pounds of tension in the bolts. Bolts are installed with Arama spring washers, with the nuts positioned against the spring washer to maintain tension and prevent loosening due to vibration. Nuts must be installed alternately on the inside and outside of the rail to ensure even distribution of forces and enhance joint stability. During maintenance, when track bolts and joint bars are removed, the joint area of the rail and the contact surface of the joint bar must be cleaned, and the joint bar and bolt threads lubricated to ensure smooth reinstallation and operation. For safety, operations over rails where all track bolts are missing or ineffective are not permitted, ensuring the integrity and stability of the rail joints. Pittsburgh, the renowned steel city in Pennsylvania, USA, witnessed a revolutionary milestone with the commencement of production at ATI Flat-Rolled Products' state-of-the-art hot strip mill. Primetals Technologies played a pivotal role by supplying the entire high-flexibility and powerful hot rolling facility. This plant significantly expanded ATI's product range to include silicon, titanium, and zirconium, made possible by 5 distinct reheating aggregates that support a wide spectrum of operations. Let's delve into the conventional coil production process. First, slabs are delivered by train directly to the furnace charging area. After identification and weighing, the slabs are alternately charged into 2 walking beam furnaces. Once hot, the slabs pass through a powerful descaler before entering the edge or rougher combination, which boasts the highest rolling forces globally. Inco panels prevent significant heat loss from transfer bars. The rotary drum crop shear separates crop cuts into 4 different sections, maximizing reuse of high-value pieces. The finishing mill was designed to handle maximum roll forces, with all 7 stands equipped with cutting-edge flatness and gauge control technology. Work roll changes are optimized using a tractor system, facilitating fully automated transport to the roll shop without the need for crane handling. The strip cooling section features laminar and turbo-laminar headers for adjustable and high cooling rates. Power coilers with 4 wrapper rolls accommodate a broad range of rolling thicknesses and widths. The pinch rolls can be exchanged in under 10 minutes with a quick exchange unit. A fully automatic modular coil shuttle system manages coil transport, with operating cars independently controlled via industrial wireless LAN to adapt flexibly to product requirements. The coil yard operates with unmanned crane operations, enhancing safety. A coil inspection line and heavy gauge cutter ensure stringent quality control. For special steel rolling, ingots are rolled into slabs for subsequent coil production or cut into plates as final products. An automatic buggy transports ingots from soaking pit furnaces to the roughing mill. From car bottom furnaces, the route continues via crane roller tables and manipulators equipped with induction furnaces for additional reheating capabilities. Hot boxes maintain specific metal temperatures after cutting with hydraulic shears, marking completion before slabs return to the yard using an automatic tag nailer. A plasma cutter is installed for plate production. An underground slab transport connects the ingot area to the furnace charging site, enabling seamless operations at this cutting-edge rolling facility. This advancement has provided ATI Allegheny Ludlam with unparalleled operational flexibility for producing top-tier, high-quality special metals.